So one thing which I wanted to tell you was this, right? There are two classes of algorithms that we will be talking about. So one of them is based on what's called dynamic programming, right? So dynamic programming. So how many of you know what dynamic programming is? I expect at least 23 hands up. And I have mechanical engineers putting their hands up, not the CS guys. Really? You don't know what dynamic programming is? Huh? Something wrong with your hand then. The essential idea behind dynamic programming is you will be using some kind of a repeated structure in the problem, right? So, and to solve the problem more efficiently, right? Suppose I have a solution that I can give for a problem of say size n, right? Then I'll try to see if I can use that for defining the solution for the problem of size n plus 1. Right? So some kind of a repeated substructure in the problems, right? A very rough way of describing what dynamic programming is, right? So for example, one way of thinking about dynamic programming is I have this game tree, right? So I look at the values of winning or the expectations of winning from all of these steps, right? I'll use these in order to compute the value of winning or the probability of winning from this state, right? So if you think about it, if from here if I am going to take say n steps, from here how many steps would you expect me to take? N minus 1 steps, right? So I look at the probability of winning when I have only n minus 1 steps left, right? I'll estimate that first. I'll use that solution for estimating the probability of winning when I have n steps left. Right, so that's essentially the idea behind dynamic programming. And so all you do now is instead of having the entire outcome and using that for estimating the probability of winning here, right, I am going to just use one step that I take through the tree, right? I use just what happens in this one step. I'll use that in order to update the probability of winning here, right? So instead of using the entire outcome, right, as in dynamic programming, in reinforcement learning methods, we will be using samples that you are getting through the state space. Okay, this is the TD method. In the other method, I explained to for tic-tac-toe, what would you do? Your sample will run all the way to the end, right? And you will use that to update. So that's the two different ways of using samples. Yeah.
So in this case, we have the updating of S of t will be determined by the value in st plus 1, yeah, right? Yeah. So the value of st plus 1 should be computed first.
Yeah.
And so since st plus 1 depends on st plus 2, again that should be computed first. So won't this be the same thing as exploring the whole all the way down and then computing
so
the value?
So let's say if you are doing it for the first time, right? The first time down the tree, there will be no updates actually. Because st plus 1 will also be 0, st will also be 0. The first time you go down, there will be no updates. But once you reach an end, then from there you will start updating the previous state. So the next time you go down the tree, then it will keep going further up.
I don't understand how this is different from updating at the end of whether you won the game or whether you lost the game.
Whether you won the game or lost the game, I actually am taking the exact outcome that happened in that particular trial, right, at that particular game, and I use that to change my probabilities, right? But here I am not just taking the outcome of that particular game, right? I am looking at the expected value of winning from the next board position, right? So if I wait till all the way here and I say I won, and I take this and update st, then I will be only updating it with the fact whether I won or not. Okay, but if I am updating it from st plus 1, see I could have reached st plus 1 multiple ways before, right? When I am doing the updation from st plus 1, it is essentially the average accumulated over all the previous trials that I will be using, right? So if I play all the way to the end and update it, it will be with a 1 or a 0. But st plus 1 could be anywhere between 1 and 0 depending on what is the probability of winning. So I will be using that value for updation. So that is the crucial difference. Right, so there are many different solution methods. So there are all these which are called temporal difference methods. So these are all different algorithms: TD lambda, Q learning, SARSA, actor critic, so on and so forth. Right, and then there is this whole search of algorithms which are called policy search algorithms. and then there is dynamic programming, and there are a whole bunch of other applications for RL. Right, so you could they're all over the place, as you could see. Optimal control, optimization, combinatorial optimization, OR, psychology, neuroscience. So that's one of the reasons I was asking, is there anyone from biotech, because biotech people do use reinforcement learning a lot, and usually there are one or two people in the RL class. So I'm just really surprised, or maybe there was a biotech registrant according to the academic website. Maybe they just gave up in CS36 and went back. I don't know. Right. So here is the most recent hot thing that came from RL. Right. More game playing, and for a change, it's not from IBM. Right. It's from Google, but the company that actually built the first this arcade game playing engine was called DeepMind, and as soon as DeepMind built a successful engine, Google bought them. Right. And so now it's Google DeepMind, but it's a separate entity, right? It's not part of Google. It's Google DeepMind operates out of London, and they're doing all kinds of interesting stuff. Many of the hot advances, very recent advances in the last year or so in reinforcement learning seem to be coming out of DeepMind. So what they did was, how many of you know about these Atari games? Right? Everyone knows about Atari games. People are getting tired. Really? No one has played Pac-Man? Yeah. How about Pong, Breakout, Space Invaders? Come on. Yeah. Anyway, so what happened was this team in the University of Alberta, okay, which put out this what they call the ALE, the arcade learning, the Atari learning environment, or arcade learning environment, which essentially they allowed computers to play these games, right? These Atari games. And what the DeepMind fellows came up with is a reinforcement learning agent that learned to play these games from scratch, right, just by looking at the screen. Okay, that's all the input it was getting, just the pixels from the screen. The raw pixels from the screen were given as inputs to it. It used a very complex neural network, so it's a deep learning deep network, right? And it is considered one of the hardest learning problems solved by a computer. And I believe it's the only computational reinforcement learning paper ever to appear in Nature, right? So usually it's very hard for non-natural science people to publish in Nature, right? Kind of obvious, right? It's usually hard for computer science folks to publish in Nature, but this was touted as a next step in trying to understand how humans process inputs, blah blah blah, things, all kinds of marketing jargon, right? But more importantly than anything else about this, it's reproducible. So I told you about, I think that's a warning sign for me to stop. So I told you about the helicopter, right? So that's basically Stanford and Berkeley are the two people who get the helicopter to fly. And I told you about the backgammon player. It's like Jerry Tesaro is the one person who gets the backgammon player to work, right? Partly because all the input features he uses in there are proprietary, but partly because it's a very hard problem to solve, right? What is the amazing thing about this Atari game engine is that these guys have released the code, right? You can, if you have enough powerful GPUs, right, you can set it up here and get it to play and get a reasonably working engine, right, that plays these Atari games. That's the amazing thing about it, that it's reproducible, as opposed to many of the other things, other success stories we've had in the past. So I do believe I have just one more slide after this, so let's see if this will work. Okay. So if you have any doubts, the green one is the learning agent. No, this just sped up for you to see. I mean, it's not like the game is progressing at the same rate, but you can see the scores though. Mind you, it was not given a reward. Okay, it is just given the screen. Okay, never got a reward for winning. You have to understand that the pixels on the top are rewarding. And if you give it rewards, it becomes cheating, right? Or is it? Yeah. Which is what they did. They did add a game over, which the ALE purists consider as cheating, but yeah, they did add a game over sign. Yeah, so the longer you keep it going, the better it is, basically. Right. I think this is getting boring. Right, so it's learnt, yeah. So this is a sequest. So you have to swim and then sink down, get some things and come up. So sequest is a game that it never learned to do greatly on though. And sequest is not something which it learned to solve well. So there are a few games like this. So when they initially published the Nature paper, I think they had like 45 or 46 out of the 50 ALE games. They were able to play well, and I think in 43 of them it had better than human performance. And I think the current state is they have like one game that doesn't play well, right? And they have better than human performance in like 48 of those games or something.